negative infinity to infinity. Then, of course, we get discrete random variables here. Discrete comes in a few different forms, okay? It can be generalized to one particular form, and we'll get to that in a second. We also have the binomials, which is another type of discrete random variable. Did everybody cover Poisson distribution? Did anybody not? Yeah, does anybody else cover hypergeometric? Okay, well, I'm going to include it anyway, but not everybody's going to have to tune in at that point unless you want to learn for the sake of learning. So anyway, it's nice to define these in terms of like a list, kind of like Jaun chapter there. We have the given, so these again, as I said, are a type of way of expressing a discrete random variable. So probability, that random variable type. Then we're going to have the mean and the variance equations. And I'm going to harp on the variance just because throwing a radical over a gigantic formula is just going to add too much little extra detail that it makes no sense. So we just reference things in terms of the variance from this point on, for this chapter at least. So, okay, that's where we saw x and p of x, where it gave you could be equal to 0, 1, 2, 3, and those probabilities could be equal to 0.2, 0.5, 0.2, 0.1 for that probability table. The mean, though, will be calculated by the summation of every x times its p of x. I might have put myself into a bit of a pickle here with this equation. So let me turn it a little bit to the side here so I can maximize my space. It's going to be the summation of every x minus the mean squared times p of x for that variance. There is another variation of an equation that I don't know if the textbook particularly goes into. Some professors, Professor Ellis, doesn't go over. But anyway, so nonetheless, if you utilize these formulas, this will carry you through that general discrete. And again, the example to go along with it, if I have x with 0, 1, and 2. Say we surveyed, I don't know, the number of people eating at a particular intimate restaurant, okay? There could be 0 people at the table, 1 person at the table, and 2 people at the table, okay? And the problem one key characteristic that you'll notice of this is that the numbers will add up to 1 or 100%. Okay? Or rather, that the summation of the p of x's equals those. You'll also notice that p of x is a number that falls between 0 and 1. So we can't have negative probabilities. Even if this does total up to 1, a negative number is times its corresponding p of x plus the next x value times its p of x. Plus the next x value times its p of x. And that would give you your mean, whatever that comes out to be. So x p of x plus x p of x plus x p of x. So I know I wrote a lot there. Okay. Yeah. All right, let me turn the page. The next one that we see, just going through that list there, was binomials. Okay, and binomials, again, it's just the way the numbers have a tendency to fall, is that they had several characteristics about them. I know that if you go into chapter 4, in the binomial, two possible outcomes. a success and a fail. Okay. The next thing is that the probability of that success, which is equal to P, and the probability of the fail, which is equal to Q, are constant, not equal. Okay. The last characteristic is that you will be taking n independent trials. Meaning that, what do I mean by the definition of this word trial? It's just whatever entity you're trying to observe. So if we're asking people a particular question, and that question has only two possible answers, a yes or a no, we define maybe the yeses as the successes and the no's, and each person is a trial. And constant from that other person. All right, we have equations that go along with this. The problem, it's going to be equal to, or rather P of x will be equal to the combinations of n choose x times P to the x times Q to the n minus x. Choose x with the parentheses, and that's not dividing the two numbers, by the way, okay? That's utilizing the combinations rule. Expanding that combinations rule out, it looks like this: n factorial over x factorial times n minus x factorial. That's the formula that we use when we're writing these out. And factorials are just numbers where you multiply every succeeding whole number integer below that number that you're looking at. So if I said 5 factorial, you were looking at 5 times 4 times 3 times 2 times 1. As far as it concerns the TI 83s or 84s, that, as I said, I don't know too much about. So, all right. So let's have a look now. So we did probability function for it. Oh, and I do apologize. If we're looking at the probability of an x being greater than, or less than, or greater than or equal to, or less than or equal to, we're going to run to these things that we have in the back of the book or printed out nice and neatly for us. Give you the mean equation for a binomial distribution. Okay, it's going to be known as mu equal to n times p. So the number of trials times the probability of success. The variance, to finish that formula list out, is going to be equal to n times p times q. Pretty straightforward. All right, we good? I'm going to turn the page. All right, let's say we're talking about, there are the probability in stats is 95%. Yeah. All right. We randomly select let's 15 students and wish to see, or okay. So let's see. Let's pull some numbers out here. As Joan was saying, utilize your givens, okay? I like to write them out on the side. So let's see, we were given a 95%, and I'm going to write that as a decimal. Okay. We were given a 15, and we were given a 12. Let's see. We're going to hopefully define this as a binomial distribution. If your professor the probability of success, we're being told that it's 95%. Okay, we can define a success as getting an A in the class. So therefore, the probability of that X, or the probability of that success, is 95%. Then we have a certain number of trials. That's going to be the 15 students that we're interviewing, or going to ask a question on. And then page, we have a probability function here, combinations of n times p to the x times q to the n minus x. So let's implement that on this question here. Okay. We've got combinations of n and x, so that's going to be combinations of 1 minus 0.95 raised to the n minus x, or the 15 minus 12 power. You can simplify that to the third power if you grab my calculator. So when you work out the combinations in this particular case of 12 and 15, you should get 455.95 raised to the 12th power So let's multiply all that out. 0.001 5404 times 455. And for the probability here, we get 0.0245 or 46. It's pretty. What? Sorry, go ahead. 455. So what I did was, you can utilize the combinations equation. I just plugged it. Which would give you 3 factorial. Okay. Seeing as these numbers work out as just being multiplied against each other, you can work this out to be 15 times 14 times 13. I'm going to stop at 12 factorial, and I'm just going to keep it there and write 12 factorial times 3 factorial. These two will cancel out, and then it's just 15 times 14 times 13 divided by 3 times 2 times 1. Divided by 6. Just go ahead and raise your hand to make sure he can see you. All right. Are we okay with the response that we got here for this one? The probability of x equaling 12 using this probability function? Okay. Good, good. How about, and there goes everything. How about if we change things up on this and we implement one of our inequalities? Greater than, let's say 10. All right, so what are we looking at here? Think of what these numbers of x are trying to entail. Greater than 10 is talking about 11, 12, 13, and 14. 10 isn't included in that because we're just looking at greater than. It's non-inclusive. Breakdown points for the x equaling a number for the equation method. But instead, we can utilize our tables instead to try and help us get to the answer a little. I'll pull the tables over here real quick, and you should have a copy of those for your test, because as far as I'm concerned, everybody needs to utilize them still. In the back of the textbook, it should be table number 2 still. The addition will be is that these tables are going to give you the probability of x being less than or equal to a number. X less than or equal to some number. They use the value k in the textbook here, so just, I guess be wary of that. That's not the k that we saw, anything like that. But the major point here is that they're looking at less than or equal to some number. So let's see, where do we go with this? We have different n values. Be the n that we're looking at. If you're given an n value of, say, 14, unfortunately, you can't use an n equals table. You're going to have to do it all by hand and utilize the equation instead, or, as I said, breaking down that equation up here into the different parts that the x values are trying to observe. But if you are lucky enough and you have those tables, definitely use them. So we're going to look at them because
is higher than 2,000. All right. So again, draw, label, find. What am I going to draw? It's a normal distribution. So start with that. So draw a normal distribution. And that flow chart, remember, x. So ignore chapter 6. We're doing chapter 5. So the average score is 1,800. My values are SAT scores in this example. And here is 2,000. So x, we can use a formula to change my x to a z-score. Of this. Okay, so we have to go from our z-scores using our table to find probability. Okay. So we have to find this area in blue. The problem, though, is our tables can't find that for us directly. What we have to use is 0, 0, about 0.4772 would go there. This area is 0.4772. That means to find the area in blue, you would just take 0.5, half the graph. 0.5 minus what you have to make every other chapter easier for you. Okay? So we're on to chapter 7 now. 6 is a very similar concept, just different formulas. What's up? So what would you like to see? Okay. Is that okay? All right, awesome. And then Francisco will do chapter 7 from this point.
all right. So now for chapters, okay, I'm going to actually blend in chapters 7 and 8, only because if you review the material itself, you see that things become a little bit redundant in terms of large sample, small sample, mean, proportion, so on and so forth. Okay. Again, those or excuse me, a confidence interval based on one sample. Okay? The equation that you're going to utilize in that case is going to be taking x bar plus minus a z critical value with alpha divided by 2 degrees of freedom times the square, excuse me, sigma over the square root of n. HT, I'm abbreviating it, again based on one sample for n is greater than or equal to 30. Your HO, your HA are going to be what we've seen before. We'll get little details in a minute. The main difference is your test statistic step, where the equation is going to be z equal to x bar minus mu over sigma divided by the square root of n. Samples to deal with in the means realm. So confidence interval based on one sample for n less than 30. Okay. Your equation is going to be x bar plus minus your critical value of t with alpha divided by 2 area and degrees of freedom. I'll get to that again in a second. Times s divided by test based on one sample again for n less than 30. And the equation that you're going to use in that case for the test statistic step, because again, that's really the only, well, I'll distinguish another small difference, is going to be t is going to be equal over s divided by the square root of n. Finding sample size. Okay, obviously we know the variable for sample n. The equation that you're going to utilize in this case, z, your critical value z, based on a certain percent confidence, squared, times sigma squared, or your variance if you want to just refer to it as that, divided by SE squared. One sample mainly because, I mean, it seems a little bit redundant to write that over and over, but we're going to see in chapter 9 where we have 2 samples worth of data, and it's going to make a, it's going to be a bit of a doozy with those equations, okay? So confidence interval based on one sample. Now this is going to be a little bit different. I'm going to distinguish this here. For n times p hat greater than or equal to 5 and n times q hat greater than or equal to 5. Okay? Not just n, but over the p hat and the q hat as well. It's one distinguishment that we have going from proportions to, going from means to proportions in terms of what the equation looks like. All right, then we have another equation that we see when we come up to the hypotheses testing based on one sample. Again, for n times p hat greater than or equal to over the square. This is where the equations differ a little bit from the confidence interval and the test statistic equation. This one's P and Q, the population parameter has, okay? It's a small distinction to make. And lastly, for chapter 8, we have our finding sample size equation. Times Q over your SE squared. Again, SE being your sampling error. And you can't see any of that because I didn't zoom out. My bad. Yes, sorry. Yeah, yep. No. Oh, 15, you are right. My apologies, sorry. 5 is... That's all the equations side of it for chapter 7 and 8. I will run through a quick little example for chapter that kind of encompasses both of them. All right, give me 1 second. All right, say, for example, there are 200. Actually, no, let's make that 27. Sounds a little bit more reasonable. Let's make that 27. I also like pizza. All right. Then we're going to say that, actually, I'm going to make it 127. Sorry, that sounds a little bit better. All right. I didn't feel comfortable with saying that. That few people liked it. So then we want all people that like pizza and our taco. So let's see. Construct, let's see, what can we do with this? Construct a what of those different things that we can do with chapter 7 and 8 are we trying to do here? Confidence interval, hypothesis test, finding a sample size. Confidence interval, I said it right there, right? Okay, so that's what you want to look into the context of the question and see what it's asking. And those keywords will be there because there's no way of masking a confidence interval with, you know, some other nomenclature or wording of it. It's literally going to say, proportions, I heard somebody whisper out there. Perfect. So let's see, we're dealing with a confidence interval based on one sample, right? There's only one sample of data that we've got here. For proportions. And the equation that we have there, as if we referred back to the previous page, is going to be p hat plus minus z alpha divided by 2 . What are we trying to estimate? The true proportion of all people that like pizza and tacos. So, the number of successes, which is 127, out of our sample of 200. So be careful that the numbers may be given to you in their raw form and not just specifically a proportion or a percentage that you can just plug right in. So they can be a little bit hidden there. I'm not going to be. How do we get that z value? Do you remember? No? We look at the percent confidence in this particular case, and the z, the critical z. In this case, 1.96. Whenever you have 95% and it's dealing with a large sample, 1.96 is your critical value, times the square root of 127 over 200. In that particular case, because when you subtract out, you get it, the p hat minus all this stuff here, and then when you add it, you get p hat plus all that stuff there. And this interval will be a 95% confidence interval estimating the true proportion of a particular population. Now, what does that mean in terms of the concept behind it? What we're looking at is the repetitiveness of a confidence interval given the string. And then 5% of the time they will not. All right. Is that it for? I mean, you want to go into chapter 9? You're good. Okay. All right. Does anybody have any questions? This is kind of a little bit cut short on an example, but are we okay with this? Where we get the numbers from? As I said, pull out those numbers, write them out. Identify what you're looking at and whether it's a confidence interval, a hypothesis test, a excuse me, a
So I'm going to finish up here, talk about chapter 9. Now, the nice thing about chapter 9, if you can do chapter 7, you can do chapter 9 too, because it's the same exact concepts, just different formulas and different situations. So let's recap. So chapter 7, we're talking about one population. And what we're saying here is that we're blank percent confidence that a true value could be the true mean, the true proportion is between these two numbers. Because when we use our formula, it's going to spit out an interval containing two numbers. Or minus something. It's still going to spit us out two numbers. But now it's going to change our interpretation a little bit. And let's make a table for that. So we can have three situations going on for our two numbers. If we get two positive numbers here, what's that telling us? Value. So we're blank percent confident that the true population mean height of UCF students is higher than the height for UF students. That's getting two positive numbers here. You could get two negative numbers. That's telling me that whatever population 1 is, that means there is no significant difference. They're about the because there's going to be a 0 somewhere here between negative and positive. So we can say we're blank percent confident that there is no significant difference between UCF and UF student heights. That's chapter 7 versus chapter 9 when it comes. Because they're both talking about hypothesis testing, and they're both a 4-step process. So for chapter 8, we're talking about one population hypothesis test, H-test. So let's just make up some numbers for an example. Maybe I want to find out if the true proportion is 0.10. Now we're almost out of time, but think of alpha as how much evidence you need to prove your claim, to suggest your claim. Now we're going to have a sample. A sample is going to give us some data, and then we can use that data, big sample. And we can use that big sample using a formula to calculate a z-score. It's the second step of this whole process. Now, rejection region, start off by drawing your graph, a normal curve. And look at what your HA is, because that'll tell you what kind of test you have. Because HA is greater than, we have a one-tailed test. And it is an upper-tailed test because it's greater. Looking up your z-table again, look up 0.40 in the body of the table, and then find the corresponding z-score. work backwards. So the closest thing I find is about 1 point. A good trick is to line up a pencil or something to find what you need. 0. We fall in the rejection region. Our conclusion rejects HO. Now p-value, you can do that too. But with time permitting, maybe it'd be good to look up p-value. But again, usually you have something minus something equals 0. Or you can have something minus something is greater than 0, less than 0, is not equal to 0. And the other big difference will be how you find this guy, your test statistic. You could use a z-score or a t-score, big sample. Four-step process for chapter 9. Okay. Now, I want to do an example, but we're out of time. But again, if you came in a little bit later, if you Google UCF, SARC, IMEO, it'll take you to a website with other videos from past sessions on them. I think there's one by myself.
This link here, it'll give you the schedule. Oh, okay. If you click on the link, it'll give you the schedule, and then you'll see that there are other statistical methods 1 sessions going on throughout the week. So hopefully there might be after your final, but that's just the way the setup was for whoever that SI leader was. They were tailoring it specifically to that class. Check that out. Then you can see here, if you're coming to any other sessions, they're going to be streamed live. Or if you click on this link here, what do you know? You're going to be taken to after saying